Welcome to what I hope will be the first installment in a series I'm calling Science for Skeptics. Before we get into the topic for today, what is science for skeptics? Maybe you've heard some people on the internet saying things like, education is indoctrination, or that science has become like a new religion, scientism, or maybe just math isn't reality. What I hope to do with this series is address these types of concerns by focusing on simple observations you can make yourself to demonstrate that the material taught in the science classroom does conform with reality. For our first topic, I plan to focus on the suggestion that buoyancy disproves gravity. I really don't intend for this to be a straw man, but this is a claim I have heard in one form or another. Specifically, we observe that helium balloons float. From this observation, can we conclude that gravity does not pull down on helium balloons? If gravity worked like the science teachers said, gravity must pull down on helium balloons. We're going to focus on empirical science here. I just mean we're going to make observations of the physical world. Theories and mathematical models can be very useful, but I think you'll agree that any model that does not match up with empirical observation is flawed. If you want to do this experiment yourself, here's what you'll need. A kitchen scale, some kind of measuring cup, some water, some ice, a pitcher or just any container to hold your water when it's not in the measuring cup, and a little plastic wrap to cover the measuring cup. Let's start with a few definitions. I was discussing this experiment with a skeptical friend of mine, and we had some difficulty over certain words. Just to try to get this out of the way, these are the meaning of the words as I will be using them. If you don't agree with these definitions, please just mentally insert the word you prefer so that we can agree on the meanings. First up, weight. I think we can agree that most things can be placed on a scale and we see that they have weight. For all the science nerds out there, like myself, I must point out that mass is different from weight. This is a nuance that would only cause arguments at this point, so for our purposes, we will be using weight as a proxy for mass. We'll be using a measuring cup to measure volume, and that will let us calculate density. You may have heard that weight and buoyancy are caused by density, and that is what we'll be investigating. Step 1. Weigh your empty cup. From experience, this was easier than trying to maintain the tare on the scale. We got 598 grams. Step 2. Add 250 milliliters of water to the cup. Record the weight. We got 846 grams. To get the weight of the water, we simply subtract the weight of the empty cup. We got 248 grams. This should let us calculate the density of the water. Just divide the weight of the water by the volume. We got 0.992 grams per milliliter. If you look up the density of water in a science book, it'll tell you 1.0, and we're within 1% of that. That seems pretty legit so far. Now this may seem a little obvious, but we'll be coming back to this again later. The cup is supporting the water. The scale is supporting the cup. The weight of the water presses down on the cup, and the cup presses down on the scale. What we've just seen here is that the weight of the water is added to the total weight of the cup. On to step 3. Set your water aside. Pour it off into a pitcher or something to save it for later. Measure out some ice. We want the same weight of ice as we had water before. And now, combine the ice and the water. How much do they weigh together? At our house, we got 1,092 grams. Recall that we had 248 grams of water, and we had 248 grams of ice. After subtracting the weight of the cup, the ice and water together weighed 494 grams. What if we just add the weight of the ice to the weight of the water? That would have come to 496 grams. Those numbers are very close, but why are they different by 2 grams? I suspect we left a little water stuck to the sides of the pitcher. That could add up to 2 grams. Now, I'd like to return to that same discussion from before. What is supporting the ice? We can see that the ice is floating. Does that mean the water has canceled out the weight of the ice? We measured the weight of the ice. It's still there, even when it's floating in the water. The ice is pushing down on the water pushes down on the cup, and the cup is pushing on the scale. As long as we've gone to all this trouble, there's more to be learned from this. Carefully measure the water level while the ice is floating in it. As you can see in the photo, the floating ice sticks up a bit above the level of the water. In our case, we found the water level had risen to exactly 500 milliliters. Be sure your ice is floating and is not touching the bottom of the glass, or this part won't work. We started with 250 milliliters of water, and when we added the ice, the water level rose to 500 milliliters. We've displaced 250 milliliters of water. Notice how the volume of the displaced water has the same weight as the ice we added. For our final observation, cover the cup to reduce evaporation and wait for the ice to melt. What do you think is going to happen? Remember, the floating ice sticks up above the water level. Will the water level rise as that ice melts? But ice is less dense than water, so the ice is going to shrink as it melts. Maybe the water level will drop. How about the weight? Once the ice is no longer floating, is the cup going to weigh more? So, how about helium balloons? Helium balloons float in the air. What supports helium balloons? We saw here in this experiment that ice floats in water because the water supports the weight of the ice. We showed that the weight of the ice was still there. Even though the ice was floating, something was still pulling it down. The water supported it, but we saw its weight on the scale. How about helium balloons then? Does the air support the helium balloon? Is there something pulling down on that helium? Is the air supporting that weight?